Yes, good morning. I would like to thank the conveners for inviting me to give this talk. I would like to take you to the completely opposite side of the world, to the river basins in high mountain Asia. So the title of my talk is Increases in River Runoff Projected for High Mountain Asia During the 21st Century. I'd like to acknowledge my co-authors, which are listed here below. And what I would like to do today is to summarize the results of two key studies that we did during the last few years. One is focusing on climate change impacts on two smaller contrasting catchments. And then I would like to move up to a much larger scale where we look at the entire Himalayas. So first, a brief overview of the area for those who are not familiar to this region. So here you see the Tibetan Plateau, the Himalayan range, and several other mountain ranges. And in this region, about 10 major river basins find their source waters. So in total, in all those river basins, 25% of the global population lives in this region and depends in varying degrees on the water that is generated from this region. So this starts here with the Siddharya and Amudarya in the western part, which both drain into the Aral Sea. And then it goes to the Indus River Basin, where we find the largest continuous irrigation scheme in the world, which is almost primarily fed by water that finds their origin in the mountain ranges here. Then we go to the more monsoon-dominated parts of Asia, the Ganges, the Irrawaddy, Salween, Mekong, and all the way up to the Yangtze and Yellow rivers in China. So what do the climate models tell us about the projected climate changes in this region? If you see that here below, you see the projected temperature changes in 2020-2050 relative to the period 1961-1990. And you see that all models, they project a rather consistent increase in temperature, although there is considerable variability. We also see that the green ones, which are the upper basins, have a projected, the temperature increase which is projected is a bit higher than for the lower basins. Then if you look at the precipitation projections, then we see that the variation is huge between the different climate models. They range from -10% to +10%, and obviously this will determine the hydrology and the future hydrological response for a very large part. So first, a bit more on the small-scale study that we've done. We've looked at two different catchments. One is the Baltoro catchment, which is located in the Karakoram mountain range in Pakistan. It has an area of about 1,400 square kilometer, a very large elevation range up to the peak of the K2 mountain, and it's about almost 50% glacierized. The precipitation is about 1,000 millimeters in this region, and there are two dominant mechanisms which provide precipitation. So there's monsoon precipitation during June to September, but there's also a considerable amount of winter precipitation in the winter season. And therefore, in this region, the glaciers, they accumulate during winter and they melt during the summer season. If we then go more towards the central Himalayas, where the climate is monsoon-dominated, we come in the Langtang catchment, which is a bit smaller. It's about 360 square kilometer, also a very large elevation range, and the same degree of glacierization. And the precipitation in this catchment is also about 1,000 millimeters, but almost all of it falls during the monsoon months between June and September. Then, without going into details, just a few snapshots of the methods we have used. So we used a 90-meter fully distributed model, and we use a degree-day factor approach to model the melt. And we've included also a very simple snow sliding model to account for avalanching, because this is a dominant process that feeds the glaciers in these areas with very steep topography. We model ice flow explicitly using a simple sliding law. We use bias-corrected era 40 era interim data. So we have quite a long historical run from 1957 to 2009. And we calibrate our results based on observed runoff, based on observed glacier extent and on flow velocity. We use an envelope-based GCM selection, which means as much that we try to cover the entire range from dry and cold GCMs to wet and warm GCMs. And we use an empirical statistical downscaling method. And we run our model from 2010 to 2100 using daily transient time series. Then what would our results show us? So first I would like to show you what happens to the glacier, then what happens to the glacial melt, and finally what happens to the overall hydrology and all components of the water balance. So first the glacier. So here on the top you see the glacier retreat around the year 2050. And you see a very large difference between the Langtang catchments, where the glaciers are relatively small, compared to the huge glaciers and the very thick ice on the tongues that we find in the Baltoro. So the Baltoro glacier responds much slower than the Langtang glacier, where you see much more rapid disintegration of the tongues and faster retreat. So on the bottom you see that trend persists, and this is the around 2100 what we project in ice depth in this region. Then a key component that we are interested in is how the melt is responding. So we've seen it, I've seen it also in earlier presentations. We are interested in when the peak melt of glacier melt occurs. Because obviously the glaciers are retreating, but the per unit area melt rates are also increasing. So this is a trade-off. And there comes a moment in time in the future when the glacier area becomes so small that this increase in melt rate cannot keep up. This is what we try to show in this plot. So here on this axis you see the glacial melt, and this is for the RCP 8.5 scenario, so which is the more extreme scenario, and this is for the RCP 4.5 scenario. And the interesting thing here is that you see that that point in time where the melt starts to, absolute melt starts to decrease, comes later in time for the RCP 8.5 scenario. And that is purely a precipitation effect, because there's the projected increases in precipitation for RCP 8.5 is higher than for RCP 4.5. So this compensates for the temperature effect. So what we see then for the RCP 8.5, that moment of peak melt will occur around 2070 and a bit earlier for the RCP 4.5. And here the dotted line you see the steady decrease in the total ice volume in the catchment. And if we go to Langtang, we don't see that compensation effect of the precipitation, because RCP 4.5 and RCP 8.5 are less diverging in terms of precipitation projections. But it's interesting to see that even in this case, that at the end of the century, the ice melt or the glacial melt is still in the same order of magnitude as we have today. So then we come to the overall changes in runoff components. So we use the full hydrological model, and what you see here is for the period 2020 to 2050 relatively to 1961, 1990, and here you see the same, but for 2070 until 2100. Then on the left side you see the case for RCP 4.5, and on the right side is the case for RCP 8.5. Now what's important to remember of this graph is that in all cases we project an increase in total runoff. But the reasons are different between the Langtang and the Baltoro. So in the Baltoro it's mostly that we have a very persistent glacial melt throughout this century, whereas in the Langtang catchment we see that there is an increase in precipitation, which is mostly the driver of this projected increase in total runoff. Then we found those fascinating results at the small scale, and we set out to see if we could also confirm these results at a much larger scale. So we used, the methods are relatively simple, so I focus a bit on where we have differences. In this case we have a resolution of 1 kilometer, and we cover the entire Himalayan range. And if you have a resolution of 1 kilometer, it's not possible to model ice flow explicitly. So we had to parameterize that, and we did that using an approach developed by Arthur Lutz, which was published in Hess in 2013, which uses a regional approach to come to future glacial extents. We also used a different forcing data set. We used the Aphrodite precipitation data set, and we used the Princeton climate data set for temperature, and we focused on a reference period of 10 years from 1998 to 2007. We also used a bit simpler downscaling method. We used a simple delta change downscaling, and we made runs up to 2050 in this case. So the first thing we wanted to try and understand is the present-day hydrology, because a lot has been written about what is the contribution of glacial melt to overall stream flow. So we tried to also express that in space. So the top panel shows the contribution of glacial melt to overall stream flow, and the thickness of the line is relative with the magnitude of the total flow, which you see here. So what you can see in terms of glacier flow is that in particularly the western part is really glacier dominated. So the Indus, this is the Indus River, we see very high percentages of glacier contribution. Then in the other regions, in particular when you go down to the monsoon dominated area, it's really rain driven and glaciers don't play a very large role. And the middle panel shows the snow contribution, and you see that the snow contribution is also in the monsoon-dominated parts relatively limited, but in some occasions, for example here, this is the Kabul River, or the upper reaches of the Brahmaputra, that snow plays a dominant role. And then the third component is the rain contribution, and you see that all along the Himalayan arc, rain is the dominant process. So then, if you look at the absolute magnitudes of the runoff that is generated, so you see here on top, these are all those components make up the total runoff. And we see that along the Himalayan arc, again, we find very high rain runoff amounts, up to, let's say, 2,000 to 2,500 millimeters a year. Then the snow runoff is relatively constant and obviously mostly concentrated in the higher parts of the catchment. And we have the glacier runoff. So the glaciers per unit area, they generate a huge amount of runoff, so it's higher than 2,500 millimeters, but the relative areas are small, and hence the average contribution on a basin scale is also limited. And here you see the base flow component, and finally you see the overall picture, and this is how the total runoff looks in our simulations. Then we've also, at this scale, we have looked at the future runoff percentages. So we've plotted here the different components in time within a year. So this is for the period 2040 to 2050. And the small blue line here, and in some graphs you can't even see it, those are the, let's say, the runoff pattern during the reference period. So what is striking on these graphs is that there are hardly any changes are projected, not even in the seasonality. There are shifts between the components, but we see a very big compensating effect. So we don't see a lot of changes in the relatively near future. So yeah, some takeaway points. I think there are very large regional differences in the importance of glacial and snowmelt. The water tower, as this region is often referred to, remains operational for decades to come, so we do not have to worry of any average water shortages in the future. But I think our challenge for the future as researchers and also for policymakers is to adapt to seasonal shifts. And the devil is really in the details in this case, I think. And also we should really focus more on modeling and understanding extreme events. Some further reading. So these are basically the two papers that I've very briefly summarized. There's a lot more to say about it, and particularly about the methods. So I can recommend to have a look at that. And then I would also like to take this opportunity to make some shameless promotion of a website we've recently released, where we want to share our results, our data, and also provide a platform for discussion on those fascinating topics. So with that, I'd like to thank you for your attention.
Thank you. We have time for a question or two? Yes.
This morning we heard a lot about the uncertainties we have in modeling snow and not to speak about glaciers. Now all the presentations you showed data were quite sure in terms of your modeling. How do you think the uncertainty will play out if you would take this into consideration, first of all in the flow components, but also in the projection?
Yeah, we've also spent obviously a considerable attention to quantifying the uncertainty, and you can find this also in the supplemental materials of those papers. But I think one of the key uncertainties is the precipitation in this region, and it's just climate models, they do such a poor job. So what we try to do is we cover the entire range of possible projections, but even the present day hydrology, still the high altitude precipitation is very uncertain. So I fully acknowledge your point. Yes.
Do you consider snowmelt in your model, snowmelt of the glacier as glacier melt? Because otherwise, I wonder why you get such super high rates of 80 to 90% or higher of glacier melt contribution to discharge.
No, I don't think it is up that high. So, but if there's snow on the glacier, we consider it as glacier melt in the large-scale model. Yeah.
Okay, thank you very much.